Hey students! Ever wondered how chemists determine the exact concentration of an unknown solution? The answer is volumetric analysis. In this 20-minute one-shot, we will master everything you need from Unit 1 of NEB Class 12 Physical Chemistry: equivalent weight, normality, molarity, primary and secondary standards, titration types, and 3 solved NEB-style numericals. This unit is guaranteed marks every year. Let us dive in. Hello students! In chemistry, we often need to know not just what substances are in a sample, but also how much of each is present. This is the difference between qualitative and quantitative analysis. Qualitative analysis identifies the components, answering the question, what is there? Quantitative analysis, on the other hand, measures the amount, answering how much is there. There are 2 main methods for this: gravimetric analysis, which measures mass, and volumetric analysis, which measures volume. In this video, we'll focus on volumetric analysis, a powerful technique that uses a process called titration. The standard setup involves a burette, which accurately dispenses a solution, a pipette for measuring a precise volume of another solution, a conical flask where the reaction occurs, and an indicator which changes color to signal the reaction's completion. A central concept in volumetric analysis is equivalent weight. Formally, it's the mass of a substance that will combine with or displace 1 mole of hydrogen atoms, or 8 grams of oxygen, which is half a mole of oxygen atoms. For elements, the formula is simple: equivalent weight equals atomic weight divided by valency. For compounds, it's a bit different. For acids, equivalent weight equals molar mass divided by basicity, which is the number of replaceable H+ ions. For bases, it is the molar mass divided by acidity, the number of replaceable OH- ions. For a salt like aluminum chloride, it's the molar mass divided by the total positive charge on the cations. Finally, for oxidizing or reducing agents, the equivalent weight is the molar mass divided by the number of electrons transferred in the balanced redox reaction. To perform calculations, we need to express the concentration of our solutions using standard units. The most common unit is molarity, with the symbol capital M, defined as the moles of solute per liter of solution. Another very important unit is normality, symbol capital N, which is defined as the number of gram equivalents of solute per liter of solution. Don't confuse these with molality, symbol small m, which is moles of solute per kilogram of solvent. For ionic compounds, we sometimes use formality. And for very dilute solutions, you might see parts per million or ppm. A crucial relationship to remember connects normality and molarity. Normality equals molarity times the n factor, where the n factor is the same term we used for equivalent weight, basicity for an acid, acidity for a base, and so on. In titration, we need a solution of a very accurately known concentration. This is called a standard solution, and it's prepared from a primary standard substance. A primary standard must be highly pure and stable so it doesn't decompose. It should also be non-hygroscopic, meaning it doesn't absorb moisture from the air, and have a high molar mass to minimize weighing errors. Excellent examples include anhydrous sodium carbonate, Na2CO3, potassium dichromate, K2Cr2O7, and oxalic acid. Substances that don't meet these criteria are called secondary standards. Their solutions must be standardized against a primary standard. Common examples are sodium hydroxide, which is hygroscopic, hydrochloric acid, which is volatile, and potassium permanganate, KMnO4, which can decompose in light. At the heart of every titration calculation is a fundamental principle called the law of chemical equivalence. This law states that at the exact point of neutralization, or the equivalence point, the number of gram equivalents of the acid is exactly equal to the number of gram equivalents of the base. For a redox reaction, it's the same idea: the equivalence of the oxidizing agent must equal the equivalence of the reducing agent. Now, how do we use this? We know that gram equivalence equals normality times volume in liters. So, for 2 solutions reacting, we can write N1V1 equals N2V2. This is the famous normality equation, and it is the backbone of all volumetric calculations you will perform. Volumetric analysis involves several techniques. The main titration types you'll encounter can be grouped into 4 categories. First, we have acid-base or neutralization titrations, like reacting a strong acid with a strong base. Second are redox titrations based on oxidation reduction. A key example is permanganate titration, which is conveniently self-indicating. Another is dichromate titration. Third, we have titrations involving iodine. Iodometric is a direct titration with iodine, while iodometric is an indirect method. Fourth are precipitation titrations, where an insoluble product is formed. Common examples include Mohr's method and Volhard's method for halide estimation. How do we know when we've reached the equivalence point? We use a chemical called an indicator. Acid-base indicators are weak organic acids or bases that change color over a specific pH range. Let's look at 2 important ones. First, phenolphthalein. It is colorless below a pH of 8.2, but turns a distinct pink color above pH 10. This makes it ideal for titrations of a weak acid with a strong base. Next is methyl orange. It is red below pH 3.1 and turns yellow above pH 4.4, so it's used in strong acid titrations. For iodine titrations, the indicator is starch, which forms an intense blue-black complex. The most important selection rule is this: the indicator's pH range must match the steep pH change around the equivalence point. Let's calculate the equivalent weight of important oxidizing agents using the N factor, which is the electrons gained or lost per molecule. The formula is equivalent weight equals molar mass divided by the N factor. For potassium permanganate, KMnO4, in an acidic medium, manganese goes from +7 to +2. This is a gain of 5 electrons, so the N factor is 5. The equivalent weight is its molar mass, 58, divided by 5, which gives 31.6. Now for potassium dichromate, K2Cr2O7. Each of the 2 chromium atoms goes from +6 to +3. That's a gain of 3 electrons per atom, so the total gain is 6 electrons. The N factor is 6. Its equivalent weight is the molar mass, 294, divided by 6, which equals 49. Hello students. Let's solve a common numerical problem from volumetric analysis. Here is the question: what is the normality of 5% W/V Na2CO3 solution? Equivalent weight of Na2CO3 is 53. First, let's identify the given information. The term 5% W/V means we have 5 grams of the solute, which is sodium carbonate, dissolved in 100 milliliters of the solution. So, our weight is 5 grams and the volume is 100 ml. The question also gives us the equivalent weight of Na2CO3 as 53. Now, we will use the formula for normality. Normality, which is capital N, is equal to the weight of the solute in grams, divided by its equivalent weight, multiplied by 1000, and divided by the volume of the solution in milliliters. Let's substitute our values into the formula. N equals 5 divided by 53 times 1000 divided by 100. This simplifies to 5 divided by 53 times 10. Calculating this, 50 divided by 53 gives us our final answer. The normality of the solution is 0.943 N. And that's how you solve it. Always start by listing your given values and then apply the correct formula. Now let's explore some advanced techniques, starting with back titration. When is this useful? Well, sometimes a direct titration is impractical. This happens if your analyte reacts too slowly, is insoluble like certain metal carbonates, or is volatile like ammonia. The process involves 3 key steps. First, you add a known excess amount of one standard reagent to your analyte. Second, you let this reaction go to completion. Finally, you titrate the unreacted excess of that first reagent with a second standard solution. This allows us to calculate how much of the first reagent was consumed by the analyte. A classic example is determining the amount of calcium carbonate in an antacid tablet. Next is the double indicator method, a clever technique for analyzing mixtures, such as a solution containing both sodium hydroxide, NaOH, and sodium carbonate, Na2CO3. First, using phenolphthalein as the indicator, we titrate with the standard acid. This first endpoint, which uses a volume we'll call V1, is reached when all the NaOH is neutralized and all the Na2CO3 is converted to sodium bicarbonate. Then, we add a few drops of methyl orange to the same solution and continue titrating. This second titration, using an additional volume V2, neutralizes the bicarbonate. By analyzing V1 and V2, we can calculate the concentrations of both original components. Volumetric analysis is far more than just a classroom experiment, it has crucial real-world applications. In industrial quality control, it ensures that pharmaceuticals contain the correct dosage and that food products have the right acidity. In environmental science, the standard method for determining water hardness is a complexometric titration using EDT, which is vital for water treatment. In food chemistry, it's used to find the iodine value of fats and oils, a measure of unsaturation, and the saponification value, which is essential for soap production. Even in medicine, principles of acid-base titration are used in blood analysis and to test milk quality. To achieve accurate results, we must be aware of potential sources of error. These fall into two main categories. First are systematic errors, which are consistent and predictable. This includes using improperly calibrated glassware, working with an impure reagent, or a persistent parallax error when reading the burette. The second category is random errors, which are unpredictable. These can arise from difficulty in judging the precise color change at the endpoint, or from minor temperature variations. To minimize these errors, you should always perform repeated titrations and average the results, use scrupulously clean glassware, and select an indicator that changes color close to the equivalence point. NEB students, let's solve our first numerical on volumetric analysis. The question states that 25 milliliters of N by 10 HCl completely neutralized 20 milliliters of NaOH solution, and we need to find the normality of the NaOH. First, let's list our knowns for the acid, which we'll call solution 1. The normality, N1, is N by 10, which equals 0.1 N. The volume, V1, is 25 milliliters. For the base, solution 2, the volume V2 is 20 milliliters, and the normality, N2, is what we need to find. For this, we will use the law of equivalence, which is a very important formula. The formula states N1V1 equals N2V2. Plugging in the values, we get 0.1 times 25 equals N2 times 20. This simplifies to 2.5 equals N2 times 20. To find N2, we divide 2.5 by 20. The final calculation gives us N2 equals 0.125 N. So, the normality of the NaOH solution is 0.125 normal. All right, let's tackle our second problem. The question asks us to calculate the equivalent weight of KMnO4, potassium permanganate, in an acidic medium. We are given that its molar mass is 158. The key here is the medium. In an acidic medium, the permanganate ion, MnO4-, undergoes reduction. The oxidation state of manganese in KMnO4 is +7. During the reaction in an acidic solution, this manganese is reduced to Mn+2, or the manganese ion. So, the change in oxidation state is the initial state, +7, minus the final state, +2, which gives us a change of 5. This means 5 electrons are gained per formula unit. The formula for equivalent weight is simple. It is the molar mass divided by the number of electrons transferred, which is our change in oxidation state. So, we substitute the values 58 divided by 5. This gives us our final answer, 31.6. Therefore, the equivalent weight of KMnO4 in acidic medium is 31.6 grams per equivalent. Hello class, let's quickly recap volumetric analysis. So to summarize, everything starts with understanding equivalent weight. Remember this key point, equivalent weight is the molecular weight divided by its N factor, which could be basicity, acidity, or total charge. From there we get our main titration formula, the one you'll use most, N1V1 equals N2V2. Don't forget the relationship between normality and molarity. Normality equals molarity times the N factor. Also, recall the difference between a primary standard like anhydrous sodium carbonate and a secondary standard like sodium hydroxide, which needs standardization. Finally, indicator selection is crucial. The indicator's pH range must overlap with the pH at the equivalence point. All right, for your NEB exam, let's talk strategy. The biggest trap is confusing molarity and normality. Always check if you need to use the N factor. So, you must memorize the N factors for common compounds. For H2SO4 it's 2, for sodium hydroxide it's 1, for anhydrous sodium carbonate it's 2. Knowing these saves so much time. The two formulas you absolutely need are N1V1 equals N2V2 and the equivalent weight formula. Year after year, NEB asks for direct numericals using this, plus definitions of standards and the correct indicator choice for a titration. Practice these questions. Stay calm, read carefully, and you will do great. You've got this. Congratulations, everyone, on finishing volumetric analysis in one shot. Always remember the core principle for titration, the normality equation, N1V1 equals N2V2. It's your key to solving almost any problem here. If this video helped you, please subscribe and like. Drop a comment with the next chapter you want to see. Coming up next is Unit 2, Ionic Equilibrium. Stay tuned and I'll see you in the next video.